It's time to talk about how we get usable energy out of the nucleus. It was discovered back in the 19th century that there were particles, positively charged particles, in the nucleus, and in about 1920, these were identified as protons, which are the same as the nuclei of hydrogen atoms. The proton is one of two kinds of nucleons, particles that make up the nucleus. The other kind, the neutron, wasn't discovered until 1932. But that was the beginning of a very productive period. If we look at how atomic nuclei are made up and held together, the first atomic nucleus, hydrogen, has just a single proton. The proton has exactly the same charge as the electron, but with the opposite sign. But it is 1,837 times more massive than the electron. The neutron is approximately the same mass as the proton, but has no electrical charge at all. Now, it works perfectly well for a single proton to serve as the nucleus of an atom and to attract the electron or electrons surrounding the atom into predictable waves. But as soon as you get two protons together, they each have the same electrical charge and they will repel. They will fly apart as fast as they can. What you need is something else to provide an additional attractive force to hold the protons together. And that something else is neutrons. We can see from later results, things that the scientists of the Manhattan Project didn't know, that both protons and neutrons are made up of similar subnucleon particles. They're not fundamental particles like electrons. They can be broken down. What they are broken down into, among other things, are little particles called quarks. Quarks always want to be in a threesome. There are always three of them, and they are held together in their little threesomes by the most powerful known force in the universe, the strong force. The force is so strong that even the little bit of it that leaks outside of a single nucleon is sufficient to attract other nucleons, whether positively charged or neutral. As a matter of fact, at short range within the nucleus, the strong nuclear force is about 140 times as strong as the electrostatic force that's trying to push these things apart. So, by adding the appropriate number of neutrons, we can achieve a stable nucleus. However, as we get higher and higher on the periodic table, that means higher and higher on the chart behind me, you'll see that there are fewer black boxes. The black boxes are the stable nuclei, till you get to the point where there are hardly any. At low atomic numbers, you need approximately one neutron per proton to stabilize a nucleus, but when you get up here, you're talking about 1.5 neutrons per proton in order to stabilize a nucleus. And these nuclei are so tentatively held together that the addition of a single additional neutron can cause a chaotic collapse of the nucleus. This is called fission. Now, if you learned about this in school, you were probably told that 1 uranium-235 fissions to one barium isotope and one krypton isotope, and that's just not true. It's not actually false, but it's only a small part of the truth. The truth is that fission is chaotic, and there are many ways that uranium-235 nucleus, for instance, can break up into smaller nuclei. When this happens, when the nucleus breaks up into two smaller ones, you have this large positive charge all in one place, and if it breaks into two smaller positive charges, they are going to repel each other with tremendous energy, approximately 200 MeV of energy, and they're going to go flying apart as fast as they can go, which is pretty fast and can do a lot of damage. In addition, there will be a few extra neutrons left over that won't fit into either of the so-called daughter nuclei. And those extra neutrons can go on and cause more fission in other uranium nuclei. So that's basically what fission is. It is a failure of the binding together of a large atomic nucleus brought on by adding a neutron to that nucleus and resulting in the expulsion of two smaller nuclei and a lot of energy. There's nothing more mysterious than that about it. It's electrostatic repulsion that you are unleashing when fission takes place, whether in a nuclear power plant or in an atom bomb.